In this video, we're going to try to take derivatives of functions or equations that are not in the form of y equals something to do with x, or f of x equals some function only of x. So we're going to have x's and y's in our equation, and maybe we won't even be able to solve for y. But that doesn't mean that we can't still take the derivative. So we just need to use a method called implicit differentiation. So we're taking the derivative, what we say, implicitly, so without actually knowing the equation for y. So I'm going to start with an example where we know how to do the derivative explicitly. So that's where we solve for y and then take the derivative like normal. So I've given you an equation here, x squared plus y squared equals 4. So this equation is written implicitly. Okay, so we don't really know what y is in terms of x. We just know that it needs to satisfy this equation. Okay, this happens to be an equation of a circle centered at the origin with radius 2. So it's not a function, actually, because it would not pass the vertical line test. But we can still find the slopes for the tangent lines. So first, we're going to write this explicitly. So what I mean is we're going to solve for y. So if I solve for y, I'm going to have y squared equals 4 minus x squared. And then I need to take the square root of both sides. When I do that, I get a plus or minus. Okay, so y, there could be positive versions and negative versions. So you could also write this as plus or minus 4 minus x squared to the 1/2 instead of the square root. Okay, so there's two different equations for y. I'm going to call it y1 is the positive one, and y2 can be the negative one. Okay, so this happens because I don't have a function. So for certain x values, I could get multiple y values. So I would have to do the derivative of each. Okay, so for y1, it's 4 minus x squared to the 1/2. So if I want to take the derivative, I need to use the chain rule. So it's something to the power 1/2. So I bring the 1/2 down, and it's going to be the same thing, something to the power negative 1/2, multiplied by the derivative of the inside, which is negative 2x. So these 2's actually cancel. And the negative would go, the negative 1/2 would move the thing to the bottom. So this would be negative x over square root 4 minus x squared. Okay, now this is for y's that are positive. Okay, so if I have positive y's, I want to use this to find the slope. Okay, so y1 is definitely bigger than 0. And now I could do the same thing for y2. So this is when the y's are negative. So I can take the derivative. It's going to look similar, but slightly different. So the negative stays, and then I have 1/2 4 minus x squared to the negative 1/2, and then multiply again by the derivative of the inside. So here the 2's go away, but also the negatives go away, and I end up with x over square root of 4 minus x squared. Okay, now again, here my y2's are less than 0. So these are negative y2's. So I get two different formulas for the slope depending on where my point is on the circle. Okay, so the circle looks like, my function looks like this. Okay, where these points are at radius 2 from the origin. Okay, so for the points on the top half of the circle, I'm going to have to use the y1 equation, and for the points on the bottom half of the circle, I have to use the y2 equation. Okay, now we could actually find this derivative implicitly. Okay, so what that means is we're going to assume that there is some function f of x so that y equals f of x. So we suppose that we can solve for y, which we did above, okay? And then we can just differentiate the entire equation, but we need to use the chain rule, okay? So since y is a function of x, let's say we want to differentiate some y term. This is actually dy dx, right? And so this is dy dx, or y prime. Okay, so this is going to be the sort of the inside derivative. So we're going to have to use the chain rule. So for example, well, let's just go below and do an example. So let's try and differentiate this by here, or maybe I'll write just here. So every time we differentiate a y term, we must multiply by y prime or dy dx. Okay, this is the derivative of the inside. So hopefully this next example will sort of indicate what I mean by that. So if we want to differentiate the same equation, what we're going to do, so if x squared plus y squared equals 4, then the derivative of this side should equal the derivative of this side. So we start by taking the derivative of both sides. So I'm going to take the derivative with respect to x of both sides, and I should get something that's equal. Okay, now on the left-hand side, when I have addition, I can do those separately. So I'm actually going to take the derivative of x squared and then take the derivative of y squared and add them up. Derivative of 4 we know is 0. Okay, now the derivative of x squared with respect to x, that's the same as what we have been doing. Okay, now here's where the problem comes in. So when I want to differentiate y squared, what I'm actually doing is taking f of x squared and trying to take the derivative. So you see that I have a function within a function. Okay, so I have the f of x is sort of my box. So I have a box squared. So the outer derivative here is going to be 2 f of x to the power 1. And then I have to multiply by the derivative of the inside. Okay, so instead of using f of x, we're going to use y. Okay, so y is like f of x. So I take the derivative of this like normal, so 2y, but then I have to remember to multiply by dy dx, or the derivative of the inside. Okay, so my y is like my f of x, okay, and the dy dx is f prime of x. So one thing to notice here, when you can tell that you need to do this, is you can see that the variable that I'm differentiating with respect to, so here it was the same as the variable I was differentiating, okay, but in the second one I'm differentiating a y, so these are different, okay, so they don't match. Oops. So when they don't match, that's when I know I need to multiply by the derivative of the inside, the dy dx, or the y prime if you want. Okay, so those are different. Okay, and then what we want to do is just solve for dy dx. So I'm going to move the 2x to the other side. So I have 2y times dy dx equals negative 2x. Divide by my 2y's. So I get dy dx is negative 2x over 2y, which is negative x over y. Okay, so that is my derivative for all points. Okay, so this derivative works for all points on the circle. So I don't need two different equations. This one will work for all of them. Okay, so maybe I should just check that. Let's use a different color. Okay, so so if we know, let's just take this. So we know we were able to solve for y. Okay, so what this says is that dy dx is actually negative x over plus or minus, okay, the square root 4 minus x squared. Okay, because that's what y was. So when y is positive, we get that dy dx is negative x over the positive square root. Okay, and that is equal to y1 prime. Okay, and when y is negative, I'm going to get dy dx is negative x over negative square root 4 minus x squared. So this is positive x over positive 4 minus x squared. And that was y2 prime when we have a positive one. So that it matches for both the positive y's and the negative y's. So this one formula will work for all points. So when we're doing this, to emphasize that y is dependent on x, that's where we usually use the dy by dx notation, okay, instead of the f prime of x. But we also use y prime sometimes. So I'll start by using dy dx, but I might switch to using y prime pretty quickly. So let's do another example. So I want to differentiate this equation. So 3x squared plus 2y equals ln of y. Now this one is hard to solve for y. So we would not want to do this explicitly. We have to do this implicitly. So what we're going to do is take the derivative of both sides. So d by dx of 3x squared plus 2 to the y should equal d by dx of ln y. Okay, now I can do the ones on the left side separately. So it's going to be d by dx of 3x squared plus the derivative with respect to x of 2 to the y should equal the derivative with respect to x of ln y. Okay, now notice in this first one, I'm differentiating with respect to x, and my equation that I'm differentiating has to do with x. Okay, now in the next one, I'm differentiating with respect to x, but my equation has to deal with y, so they're different. And the same on the other side. So I'm differentiating with respect to x, but the thing I'm differentiating is actually of a y. So when we take the derivative, the first one we can do like normal, so it's just going to be 6x. But when I do the second one, I want to do the outer derivative, so that's the derivative with respect to y. So that's going to be for 2 to the y, it's 2 to the y times ln 2. Okay, but then I have to remember to multiply by the inside derivative, which is actually dy dx, or y prime. Okay, same over here. So if I want to differentiate ln y, the outer derivative is 1 over y, because that's the derivative of ln. But then I have to times by dy dx. Okay, so let me just write here. So this is like the outer derivative, and this is the inner derivative. Okay, so this is the outer, and this is the inner. So we're using the chain rule for both. And now what we want to do is solve for dy dx. So I want to put them on the same side. So I'm going to have 2 to the y ln 2 times dy dx minus 1 over y dy dx is equal to negative 6x. So I moved this term to that side by subtracting, and this term to that side also by subtracting. Okay, now I can factor out the dy dx from the left side, and I have 2 to the y ln 2 minus 1 over y, and that should be equal to negative 6x. And then I can divide by that, so dy dx should be negative 6x over 2 to the y ln 2 minus 1 over y. Now, you can leave it like that, or because we don't usually like fractions within fractions, I'm going to multiply by y over y. Okay, so when I do the bottom, I have to go to both terms here. And that's going to simplify or make my derivative look a bit nicer. So dy dx is going to be negative 6xy divided by 2 to the y times ln 2 minus 1. So now I don't have any fractions within fractions. So that looks a bit nicer. Okay, so the method that we just used, so to determine dy dx for an equation that has both x's and y's, what we want to do is differentiate both sides. Okay, so differentiate both sides of the equation with respect to x. Okay, so or t maybe, depend your independent variable. Okay, and then we want to just make a note. So if you're differentiating something with y, we want to remember that terms with a y involve the chain rule. So they have hidden, okay, so they have hidden x values. So that means that when you take the derivative, you need the chain rule. So you want to multiply by y prime or dy dx. And then what we want to do, we're just basically here for steps 2 and 3. I could just write solve for dy dx, okay, or y prime, whatever you're using. But to make it a bit more explicit, we want to collect the dy dx or the y primes, whatever you're using, okay, on one side of the equation. Okay, and factor it out. And then we're going to divide by the thing that we have left over on both sides. Okay, so that's the idea. Let's just do a couple more examples here. Okay, so here we want to differentiate x squared plus xe to the y equals 2. So we differentiate both sides with respect to x. Okay, so on the left side, we can do these separately. Okay, on the right, we know this is 0 because it's a constant. So here, okay, we're taking the first one, we're taking the derivative with respect to x, and everything in our brackets that we're taking the derivative of is dependent on x only. Okay, now over here, we're taking the derivative with respect to x. One of the things has x's, but it's multiplied by something that has y's. So remember, y's have hidden x's. Okay, so in order to take the derivative here, we actually need the product rule. Okay, so here's our first function, here's our second function. Okay, so we want to be careful there. So the first one, this is normal, so we just take the derivative is 2x. For the second one, though, we're going to do the derivative of the first function times the second function as it is, plus the derivative of the second function times the first function as it is. So that's using the product rule. Okay, and now I have taking the derivative with respect to x, and the thing I'm differentiating has only x's, or I'm taking the derivative with respect to x, and the thing has only y's. So I'm going to have 2x plus derivative of x is 1. Now for this term, this e to the y, notice that we're not taking the derivative. So I don't need to multiply here by dy dx or y prime. It's just e to the y. Okay, there's no derivative there. Over here, though, now we are taking the derivative. Okay, so the outer derivative is the derivative of e to the y, which is just e to the y. Okay, so this is the outer derivative. So we're using the chain rule. So I want to remember to multiply by dy dx. I'm going to use y prime here. Okay, so this is the inner derivative. Okay, and then I have to multiply by the first function, which is an x. Okay, so now I just want to solve for y prime. Okay, there's only one term that has a y prime, so I'm just going to move these terms to the other side. Okay, so we have y prime times e to the y x is equal to negative 2x plus e to the y. Oh, I'm sorry, minus. I need to subtract both of them over. And now I can just divide by x e to the y to get that y prime is negative 2x minus e to the y over x times e to the y. So that's my derivative. Okay, one more example. So here we want the equation for the tangent line. Okay, so that means that we first want to find the slope. Okay, so m, the slope, is going to be the derivative dy dx, okay, evaluated at the point. Okay, so that's x is 2 and y is 4. So we're going to start by taking the derivative. So we're going to take the derivative implicitly, because if you look at the equation, it's hard to solve for y here. So I have a y cubed, and I also have this term with x's and y's. Okay, so it's not easy to solve for y. So we're going to take the derivative implicitly. So I'm going to just take the derivative of each term, so or both sides. So derivative of x cubed plus the derivative of y cubed should equal the derivative of 9xy. So here I have x's and x's, so that's a normal derivative. The next one I have x's and y's, okay, so that needs the chain rule. And in this one I have x's and something to do with x's, but also something to do with y's. Okay, so that one I'm going to need the product rule, because there's x's times y's, and the y's have hidden x's, and I'm going to split it into 9x times y, or you could do x times 9y, or you could pull the 9 right up front. Okay, it doesn't matter. So when I take the derivative, this first one is going to be 3x squared. Okay, now the second one, I take the derivative of the outside, so that's 3y squared, but then I have to multiply by the dy dx, the inner derivative. So here I'm going to write out the chain rule, or the product rule, sorry. So I'm going to have the derivative of 9x times y plus the derivative of y times 9x. Okay, so let's just compute those derivatives. So the derivative of 9x, okay, so x and x's, okay, that's good. Over here I have x's and y's. Okay, so the derivative of 9x is just 9. And here, this y, we're not taking the derivative, so it's just y. We don't need a y prime there. The next one, we are taking a derivative. The derivative of y is 1, okay, because it's just like the derivative of x is 1 when you have an x. Okay, so the outer derivative is 1, but then I want to multiply by dy dx, and then I still have that 9x there. Okay, so now I see that this term has a dy dx, as does this term. So I want those terms on the same side. Okay, so I'm going to move this one over here, and I'm going to move this term over here. Okay, so that means that I'm going to have 3y squared times dy dx minus 9x times dy dx equals 9y minus 3x squared. So then I can factor out the dy dx over here. Okay, so then I have 3y squared minus 9x equals 9y minus 3x squared, which means that my dy dx is going to be 9y minus 3x squared over 3y squared minus 9x, which I could factor out a 3 from everything to make things a bit nicer. So I get that my derivative is 3y minus x squared over y squared minus 3x. Okay, so so there is my derivative. Now, the slope was the derivative evaluated when x is 2 and y is 4, right? That's our point, 2, 4. So I plug in both of those. So 4 for y, so I have 3 times 4, and 2 for x, minus 2 squared. And then I have 4 squared minus 3 times 2. So that's 12 minus 4 over 16 minus 6. So I get 8 over 10, which is 4 over 5 if we simplify. Now I should make a note here, at this point here, okay, so as of here, we're done differentiating. Well, okay, maybe I should say here. So this is the last step where we were still taking derivatives. So at this point, we're done taking derivatives. If you want, you can plug in your values right at this point and then solve for dy dx with only numbers around. That's totally fine because we only want the derivative at that point. But I find it sometimes useful to solve for the derivative completely and then plug in the points. Okay, but it's up to you. So maybe I'll just make a little note here. At this point, we're done differentiating. So we could plug in x equals 2 and y equals 4 at that point, but no earlier. Okay, so at the step before, we were still computing derivatives. So we need to compute those derivatives before we plug anything in. Okay, so we wanted the equation, so we know that the slope is 4 over 5, and we know that it goes through the point 2, 4. So the equation is going to be y minus 4 is 4/5 x minus 2. So that's in point slope form. Or if you want to solve for y, it's going to be 4 over 5x minus 8 over 5 plus 4 is going to give you 12 over 5, I think. Okay, so this is the equation in slope-intercept form. Okay, but this is also an equation. of the tangent line. Okay, it's in a different form, it looks different, but they're the same line. Okay, so either of those answers will be fine if it doesn't tell you how to give your answer, which here it doesn't. Okay, so either of these are fine, but to find the slope we need the derivative, and here we had to do the derivative implicitly.